Good day, students. Our lecture today is on hopper design. Hopper is usually used as a short-term storage for raw materials, intermediates, and products in the form of particulate solids in a process plant. Interruption of flow from discharge hopper may frequently be responsible for production halt. Therefore, hoppers should be designed to ensure flow of the intended particles or powder. Hopper design is a wide subject. In this lecture, we only cover design philosophy to ensure flow from conical hoppers when required. In hopper design, the four big questions are: what is the appropriate flow mode? Hopper angle? How large is the outlet for a reliable flow? And what type of discharger is required? And what is the discharge rate? So let's look at these elements. First, let's look into hopper flow modes that are available. So the main hopper flow modes that has been identified are mass flow and core or funnel flow. So in mass flow, all the materials in the hopper is in motion. So when we open the discharge orifice, all the materials will start to move, but not necessarily at the same velocity. Not all layers or all particles will be moving at the same velocity. In core or funnel flow, the central part will be moving and the sides will be dead. Then we have another flow mode, which is expanded flow, and this is a combination of mass flow cone with funnel flow above it. So this is a diagram of core flow or funnel flow and mass flow. In core flow, the solids at the top will start moving first once the discharge orifice is opened. So the sides will remain stationary. There's only contact between these particles and these particles. Okay. So once it will empty from the top. So once all these powders are out, so finally these powders here will be discharged. So this is core or funnel flow. In mass flow, all particles will start moving at the same time at different velocity. So these particles will have particles interaction, as well as particles moving along the wall of the hopper or silo. Okay. So this is the graphical image of the core flow and mass flow. So in mass flow, these lines, if you notice, as they go down, it moves as a straight line until it reaches the cone. So this is the conical part. Okay, so this is called the silo, the straight one. Okay, so it moves in a straight line until it reaches the conical part, and then still the lower part of the material stored will be discharged first. So it follows its turn, okay, until finally all the particles are discharged. As in core flow pattern, if you have particles with different layers, the middle part will start to flow first. So it will start flowing out, and then finally is the first layer that went in will be the last layer to leave the hopper. As for expanded flow, it is a combination of mass flow at the bottom here, because the cone is not a direct cone, so it has a cone shape here and then a narrowed discharge point here. So there will be a mass flow here and a funnel flow taking place at this area. So that is expanded flow. These are a list of characteristics of mass flow. So in a mass flow, the motion of powder is uniform. So it moves uniformly and at steady state. And the bulk density of the discharge powder is constant and independent of the silo height. Stresses among the solids are low, so there are low compaction of powder, so it actually allows smooth movement of powders. There is no stagnant regions in a mass flow, and the risk of product degradation is also small compared with core flow. The first in, first out flow pattern of mass flow hopper ensures narrow range of residence time for solids in the silo. So the first product that came in will be the first product that goes out. So, and we will start, that will be used first. So that means we don't store a product for extended period. Okay. And then segregation of particles according to size is also less of a problem in mass flow. However, the friction between moving solids and hopper walls can result in erosion of walls. And then when there's erosion of walls, this can give rise to contamination of solids by the material of the hopper wall, as well as it can also cause degradation of the hopper wall. So that will require some mechanical repairing as well. So when erosion becomes a problem, when that powder usually causes erosion, it doesn't get along very well with the material of the hopper, then we can consider core flow for that particular powder production, powder used in production. Let's look into the second question, which is hopper angle. For conical hopper, the slope angle required to ensure mass flow depends on powder-powder friction and powder wall friction. So a hopper which gives mass flow with one powder may give a core flow with another. So if we look at this figure, as the compaction stress increases, the strength of the powder increases. So this is for a weak powder. As the compaction increases, the strength of the powder increases faster. And this is for strong powder, which is cohesive, which is easily flowable powder. Okay. So this one, the strength, when we change the compacting strength, when there's a small change, there's also a small change in the strength of the powder. So what does this strength of the powder do to affect a flow from hopper? So it actually produces arching in the flow. So if this arch, as it builds up, so when you have powders here, when small powders settles, and then as it builds up, so it will start to compact one another. So when the compaction increases, so once the strength is higher than the strength among the flowing powders, so the arching will happen and flow will be stopped. If the strength of the powders which are flowing are stronger, The arch will form, but it will collapse because this side is stronger than the arch itself. So the flow will still continue to happen. So the Hopper flow factor FF relates the stress developed in a particulate solid with the compacting stress acting in a particular hopper. So it's so the flow factor FF is just a ratio. Okay, so a high value of FF means low flowability. Why? Because high compacting stress factor means greater compaction. A low value of stress in powder means more chance of an arch forming. So high value of stress, compacting stress, and low value of stress in powder will give you high value of Hopper flow factor. Okay, so that's why high value means the flow will not happen because there is an arch. So Hopper flow factor depends on nature of the solid, nature of the wall material, and slope of the hopper wall. The Hopper flow factor can also be associated with yield stress. Okay, yield stress is a stress which causes flow. That means it allows flow. So the powder in the exposed surface of the arch is sigma y, which is also known as unconfined yield stress of the powder. So if the stresses developed in the powder forming the arch are greater than the unconfined yield stress, flow will occur. Okay, so if the powder stress is bigger than the unconfined yield stress, so the flow will occur. If we look back to the slides, so this is where the unconfined yield stress is, and this is where the powder stresses are. So obviously, if these stresses are stronger, the powder will flow. This criterion can be rewritten as this. Okay, so this sigma D is replaced by sigma C over flow factor. So the unconfined yield stress of the solids varies with the compacting stresses of different powders. So this yield stress is a function of the compacting stress of a specific powder. So let's look into the critical flow condition. The limiting condition for flow is when sigma C over flow factor is equals to sigma y, the unconfined yield stress. So let's look at this figure 10.7. This is a plot of stress developed, which is sigma D, or unconfined yield stress, which is sigma y, against compacting stress sigma C. So this is the same graph as we have same figure that we have seen previously. It's this graph. Okay, this figure will actually tell us at which condition flow will occur for a specific powder in the hopper. If let's say the powder has a yield stress, okay, either sigma y or sigma d, greater than sigma c over ff. Okay, that means if it is greater than this line, so this line indicates when it's equals. So if the yield stress is greater than this value, which is actually A, no flow will occur. That is the flow function for powder A. If the powder has a yield stress lesser than sigma c over ff, which is function C, the flow occurs. Now let's look at powder B. Okay, powder B has a critical condition, this point, because it coincides with the limiting condition of flow when it's equals to. So at this point, the unconfined yield stress is equal to stress developed in the powder. So therefore, if actual stress developed is smaller than the critical flow, okay, when it's smaller, then there is no flow. If it is bigger, then there is flow. Okay, so that is the condition with powder B. The third big question in the hopper design is outlet size. So the stress developed in the arch is related to the size of the hopper outlet, which is termed as B, and the bulk density of the powder. So a minimum outlet dimension of the hopper is defined by this equation, and the parameters are, if you can see, there is a sigma critical, and then there is a gravitational flow, and then there is density of particles, as well as h theta. So what is h theta? H theta is the factor determined by the slope of the hopper wall. So the slope that we determine, because it's conical in shape, right? So there will be a slope angle. So that is h theta. And h theta can be estimated using this equation. So this is particularly for conical hoppers. This slide gives a summary of a conical hopper design. If you notice, we did not discuss the big question 4, which is discharge, how the particles will be discharged and what is the discharge rate. So that is not discussed in this lecture. So we have only discussed up until the first 3 big questions. Okay, so in summary, the relationship between strength of powder in the arch, the unconfined yield strength, with compacting strength acting on the powder plays an important role on the flow characteristics of the powder. So variation of hopper flow factor is affected by nature of the powder, nature of the hopper wall, slope of the hopper wall. Hopper flow factor is a function of powder properties as well as the hopper properties. And knowing the hopper flow factor and powder flow function, critical stresses in the arch can be determined and minimum size of the outlet can be found. So to design a hopper, we need to measure the powder cohesiveness, which gives us the interparticle friction, wall friction, the powder and wall friction, compressibility and permeability of the powder. And then we calculate the outlet size, hopper angle for mass flow, and the discharge rate. So this one is not covered in this lecture, so you're expected to know up until this part. Let's look into the worked example to understand how we use the equations that we have discussed in designing the hopper. So the question states, shear cells test on a powder gives the following information. So we have a kinematic angle, effective angle of internal friction is 40 degrees. Kinematic angle is this one, 16 degree. Bulk density 2000, and the powder flow function is represented by this. Alright, so determine the maximum semi-included angle of a conical mined steel hopper that will confidently ensure flow, and minimum diameter of the outlet. Right, we have not discussed this part, the semi-included angle, in the lecture part, so I'll show you in this tutorial, in this question, how we find the semi-included angle. This is actually the H theta. So we are going to find this theta value, and then we are going to solve for the minimum diameter of the circular outlet. To do that, we need a set of figures, which I'm going to show you now, and it is actually present in the appendix part of the lecture. Okay, it's here. So there are, it's actually known as hopper flow factor values for conical channels at different angles. So we have one figure for 30 degrees, one for 40 degrees, and then one for 50, and another for 60. So if you notice, these are the flow factors, and then this is A. So this is for when the conical channel has a effective angle of internal friction, which is 30 degrees. So this is the theta. Okay, so this is the semi-included angle of a conical part. Okay, the theta and the H theta, and this is the psi W is the kinematic angle of wall friction. Okay, so if we know this value and we know the flow factor, we can find the theta value. Okay, that's what we are going to do for the example question. Right, since the question mentioned that the internal friction angle is 40 degrees, so we will be using the figure of 40 degrees, okay, which is figure B. 40 degrees is figure 10.18B. So it's given the kinematic angle is 16 degrees, so this is about 16 degrees. So we draw a line until we touch flow factor value. Okay, and then we give a safety margin. Okay, so there should be a 30 degrees safety margin. So we obtain the hopper flow factor as 15 because it only crosses the FF15 at all points, right? And the semi-included angle for mass flow is 30 degrees. Okay, so now we have identified the theta. So that is the answer for the question of the maximum semi-included angle of a conical mined steel hopper that will confidently ensure mass flow. So that is the answer. So theta is 30 degrees. So now with that answer, we can calculate the part B, minimum diameter of circular outlet to ensure flow when the outlet is opened. So we use this equation, and so we have a function here given. So if we substitute the sigma c, so we get this. So the critical value of unconfined yield stress is found when it is equals. Okay, this symbol here should be equal. So why are we looking for critical value? Because the equation for minimum outlet diameter requires the critical value. So then we solve for critical value, and then we also calculate the h theta. So at theta is equals to 30, the h solves to 2.5, and then we can find B. Okay, therefore the mass flow without blockages can happen when the semi-included cone angle is 30 degree and a circular outlet diameter is at least 23.4 cm. In the final parts of the lecture, I've included the problems that can occur in hoppers. So we can have these problems happening in a hopper. So let's look into each one of it. So we can have rattling or piping. So this is the core flow. So this is where the void is, where the particles are keep moving, and this powders here continues to be stagnant. That's rat holing or piping. There's a YouTube video link that I've attached at the end of the slides for you to watch. So one of the YouTube video shows rat holing animation. Then funnel flow. Okay, so in funnel flow, segregation can happen. So if we put in a mixed powder, so the coarser ones will build up and the finer ones may be flowing down. Okay, so this can happen. Arching and doming, so this is what we studied just now. So we can have arching, where especially when the powders are very fine. Then we can have insufficient flow. So this could be when the outlet size is too small. We can have flushing when the outlet size is too big. We can have inadequate emptying, which means every time we empty our hopper, these parts just remains. Okay, so this one can cause quality issue. And then mechanical arching. So this is similar to traffic jam at the outlet of bin. So too many large particles are competing for the small outlet. So this can cause mechanical arching. And time consolidation or caking. So many powders will tend to cake as a function of time, humidity, and pressure and temperature. So this one is like example is Milo. So if let's say Milo is passing through a funnel, and then if there are some Milo particles that are left in a funnel, after some time it will attract humidity and it can actually start caking, building up and sticking to the wall. Okay, so this can also happen. So these are the problems that can happen in a storage bin or hopper, we call it, right? So these are some YouTube videos, interesting YouTube videos that you can watch that explains about the hopper flow. So this one is on coring funnel or core flow. So sorry, this one is on core flow, this one is on mass flow, and this one is on rat holing. So enjoy watching the videos, and these are the appendix which are also present in your textbook. okay, for different angle values. Right, that's all for hopper design. See you in the next lecture.